Somewhere inside a research facility in Kawasaki, Japan just quietly rewrote the rules of the global quantum race. No fireworks, no dramatic press conference, just a technical roadmap update that most people scrolled past without realizing what it actually meant. But if you understand what Fujitsu and Riken just committed to, you'll see why intelligence agencies, chip manufacturers, and rival governments across Asia are suddenly paying very close attention. This is not just another company promising a bigger computer. This is a nation-state level bet that could decide who encryption and industrial power. And the ripple effects are already spreading across China, South Korea, the United States, and every country that thought it had a comfortable lead in quantum technology. For years, the quantum computing conversation was dominated by American names: Google's Sycamore chip, IBM's roadmap toward 1 million qubits, a handful of well-funded startups in California and Colorado chasing headlines about quantum supremacy. Japan, by comparison, was treated almost like a footnote, a country with a strong engineering culture, but no real appetite for the moonshot bets that quantum computing demands. That perception just became outdated. Japan has spent the last 2 years quietly building the deepest public-private quantum partnership on the planet, and the latest roadmap update from Fujitsu confirms that Tokyo is not playing catch-up anymore. It is trying to leapfrog everyone else by skipping straight to the hardest, most valuable part of the problem: fault tolerance. Let's start with the headline number because it is genuinely staggering. Fujitsu, working alongside Japan's Riken Research Institute, has committed to building a superconducting quantum computer with more than 10,000 physical qubits by fiscal year 2030. That target alone would make it one of the largest superconducting quantum systems ever attempted anywhere in the world. But raw qubit count is not the part that should catch your attention. The real story is what Fujitsu wants those 10,000 physical qubits to produce: 250 logical qubits, capable of early fault-tolerant computation. That distinction between physical and logical qubits is the single most important concept in this entire story. So let's slow down and actually explain it. A physical qubit is the raw hardware unit, a tiny superconducting circuit cooled to near absolute zero, vibrating with quantum information that is incredibly fragile. Physical qubits are noisy. They lose their quantum state within microseconds. A stray vibration, a temperature fluctuation, even cosmic rays can corrupt the information they're holding. That's why today's quantum computers, even the flashy ones you read about in tech headlines, can't actually do much useful work yet. They're powerful in theory, but unreliable in practice, like a stadium full of 5-year-olds trying to whisper a message in perfect unison down a very long line. A logical qubit is different. It's built by combining dozens, sometimes hundreds of physical qubits together using quantum error correction, creating a single unit of information that is protected against noise and decoherence. Logical qubits are what actually let quantum computers run long, complex, useful algorithms without the calculation collapsing into garbage halfway through. The entire quantum computing industry has quietly admitted that logical qubits, not physical qubit counts, are the real scoreboard. And that's exactly the scoreboard Japan just decided to play on aggressively. Fujitsu's approach to this problem has a name: the STAR architecture. It stands for an early-stage fault-tolerant quantum computing framework, developed in close collaboration with Osaka University, designed specifically to squeeze meaningful, error-corrected computation out of a smaller number of physical qubits than competing approaches typically require. In plain language, Fujitsu is betting that it can get to genuinely useful quantum computing faster by being smarter about architecture, rather than simply chasing bigger and bigger raw qubit counts the way some Western companies have done. It's a classic Japanese engineering philosophy applied to one of the hardest problems in physics: efficiency and precision over brute force. This isn't a startup's fantasy roadmap either. Fujitsu already has receipts. In April 2025, the company unveiled a 256-qubit superconducting quantum computer, a 4-fold jump from its previous 64-qubit system, built at the Riken Fujitsu Collaboration Center in Waco. That facility has become the beating heart of Japan's quantum ambitions, a place where academic researchers and corporate engineers work side by side instead of in separate silos, something that has historically slowed down quantum progress in other countries, where university labs and private industry rarely move at the same speed. And Fujitsu isn't stopping at 10,000 qubits either. The roadmap extends well beyond 2030. After the early fault-tolerant milestone, the company plans to pursue research integrating superconducting qubits with an entirely different technology: diamond spin-based qubits, developed in partnership with Delft University of Technology and the Q-Tech Research Institute in the Netherlands. The long-term target is 1,000 logical qubits by fiscal year 2035, using a hybrid architecture where superconducting qubits handle fast, high-fidelity local operations, while photonic and diamond spin qubits handle long-distance entanglement and interconnection between separate quantum processors. If that sounds complicated, that's because it is. But it also reveals something important. Japan is not betting on a single quantum technology. It's building a modular, multi-technology ecosystem designed to scale in ways that a single architecture approach simply cannot. Now here's where this stops being just a corporate story and becomes a national one. This entire roadmap sits inside a much bigger government structure. Japan's Cabinet Office runs something called the Moonshot Research and Development Program, and Goal 6 of that program funnels roughly 100 billion yen specifically into fault-tolerant quantum computing research. That's single. Funding stream is the financial foundation underneath the Riken Fujitsu 10,000 qubit roadmap. Layer on top of that, the Q-LEAP flagship program, a Ministry of Education initiative that has poured more than 30 billion yen into quantum computing, sensing, and communications research since 2018. And you start to see the shape of a coordinated national strategy rather than one company's side project. Prime Minister Ishiba's government took things even further in 2025, formally declaring it the first year of quantum industrialization in Japan. That's not just a slogan. It came with real money attached, a headline research and development budget of roughly 1.05 trillion yen, covering both semiconductor and quantum technology combined, with an estimated $900 million specifically directed at quantum-focused programs. On top of that, the government carved out 50 billion yen, worth roughly $335 million, specifically to back more than 10 Japanese quantum startups, including names like KDDI, OptQC, and JAIJ, alongside the Fujitsu Riken effort. This is what a serious industrial policy looks like when a government decides a technology is too important to leave entirely to private capital. And the ambition doesn't stop at building bigger machines. Japan has set a public target of creating 10 million quantum users and building what officials describe as a quantum-driven economy by 2030. It signals that Japan isn't just trying to win a scientific prestige race. It's trying to build quantum computing into everyday industrial and commercial infrastructure the same way it once did with robotics and precision manufacturing. Whole economy quietly becomes dependent on it, and therefore built around Japanese quantum architecture. This is where the story stops being about physics and starts being about geopolitics. Because Japan is not moving in isolation. It's one player in an increasingly intense four-way race across Asia, and every other major player just watched Fujitsu's roadmap update land, with a very different reaction than a simple technology announcement usually gets. Start with China, because China's approach to quantum computing looks nothing like the collaborative, semi-transparent model Japan is running. Quantum technology sits inside China's 14th five-year plan as a formally designated strategic priority, a status that puts it in the same policy tier as semiconductors and artificial intelligence. Chinese investment in quantum research is widely described by analysts as dwarfing every other nation's spending, though because so much of it flows through state-directed channels and military-adjacent research institutes. The real total is difficult for outside observers to verify with precision. What is clear is that Chinese leadership, going back to direct statements from President Xi Jinping emphasizing the strategic urgency of quantum science, treats this technology as inseparable from national security and long-term competitiveness with the United States. That framing matters enormously when you think about why Japan's roadmap update is landing the way it is. Japan sits geographically and politically in the middle of an escalating technology rivalry between the United States and China, much the same way it does with semiconductors. A credible, homegrown, fault-tolerant quantum. Computing capability doesn't just give Japan bragging rights. It gives Tokyo genuine strategic leverage, a seat at the table as an independent technological power, rather than simply a subcontractor to whichever superpower currently leads the field. That's precisely why this roadmap update is being read in policy circles as a signal of intent, not just an engineering milestone. Now bring South Korea into the picture, because Seoul's response over the past year has been anything but passive. South Korea has committed approximately $2.3 billion, roughly 3 trillion won, toward quantum computing development through 2035, in what analysts are now calling the K-quantum strategy. Unlike Japan's heavily domestic, Riken Fujitsu-centered approach, Korea's model leans more on international partnerships. IonQ has deployed a 100-qubit tempo system at the Korea Institute of Science and Technology Information. IBM's quantum systems are hosted inside Korean research facilities. Samsung, LG, and SK Telecom are all involved at various levels, alongside a growing footprint from European quantum companies like Pascal. Korea has also formally established a Korea-US Quantum Technology Cooperation Center and launched an international collaboration initiative called INCO-Q to bring in foreign researchers and joint projects. Analysts who track the region closely now describe South Korea as the most aggressive quantum follower in Asia, a country positioning itself less as a peripheral participant and more as a genuine strategic challenger to Japan's head start. But here's the tension underneath that strategy. Korea's major quantum partnerships run almost entirely through American firms, which means future US export restrictions on quantum technology bound for China could end up complicating Korean firms' commercial expansion across the rest of Asia. Japan, by building more of its core architecture domestically through Fujitsu and Riken, is partially insulating itself from exactly that kind of geopolitical exposure. This is the part most casual tech coverage completely misses. The quantum race in Asia isn't just China versus everyone else, it's Japan and South Korea essentially running two different strategic philosophies against each other in real time. Japan is betting on deep, vertically integrated domestic capability, controlling the entire stack from qubit fabrication to software, the same instinct that built its automotive and electronics dominance in the 20th century. South Korea is betting on speed through international partnership, importing proven Western hardware and layering Korean industrial application on top of it. Neither approach is obviously wrong, but only one of them produces a country that can credibly claim to have built its own fault-tolerant quantum computer from the ground up, and that distinction is going to matter enormously once quantum computing starts intersecting with national security. Which brings us to the topic that should genuinely worry anyone paying attention to cybersecurity: encryption. This is arguably the single most consequential implication of the entire quantum race, and it's the part almost nobody outside the industry properly understands. Most of the encryption protecting your bank transactions, your government communications, your corporate secrets, and honestly, the entire structure of digital trust worldwide relies on mathematical problems that are extremely difficult for classical computers to solve. Things like factoring enormous prime numbers. A sufficiently powerful, fault-tolerant quantum computer running an algorithm developed decades ago by mathematician Peter Shor could theoretically break that encryption in a fraction of the time it would take every classical computer on Earth working together. This is exactly why the phrase used at industry conferences like Q2B Tokyo has shifted noticeably over the past year, reflecting a broader change in how seriously the entire industry now treats this threat. Executives are no longer talking about quantum computing merely breaking encryption someday. They're talking about quantum computing redefining digital trust itself, arguing that the real challenge isn't just adopting new post-quantum algorithms on paper, but engineering confidence across the entire communication stack, from photonic links and quantum key distribution systems all the way to AI native cloud infrastructure and next-generation 6G networks. That's a much bigger, scarier problem than simply swapping out one encryption algorithm for another, because it means every layer of digital infrastructure eventually needs to be quantum resistant, not just the login screen. Governments already understand this, which is exactly why so much of the funding behind Japan's roadmap and China's parallel effort and America's own national quantum initiative isn't just about economic competitiveness, it's about a race against the clock on cryptography. Intelligence agencies around the world operate under something security researchers call a harvest, now decrypt later strategy. Adversaries are already collecting encrypted data today, betting that a future fault-tolerant quantum computer will let them retroactively decrypt it once the hardware finally catches up. That means the sensitive government communications, financial records, and classified data being encrypted right now in 2026 could theoretically become readable the moment any country crosses the fault tolerance threshold Fujitsu is racing toward. Whoever gets there first doesn't just win a scientific prize. They potentially gain a temporary window where they can read encrypted traffic that every other government on Earth still believes is secure. That single fact is why Japan's roadmap update isn't being treated as a corporate press release inside defense and intelligence circles. It's being treated as a national security data point. If you're going to make a video about geopolitics or cybersecurity later this month, this is the thread worth pulling on because it connects directly back to everything we're covering right now about who controls fault-tolerant quantum computing first. By the way, if you're finding this kind of deep technology breakdown useful, go ahead and hit subscribe because we're covering the entire global quantum race across multiple upcoming videos, and you won't want to miss where this story goes next. Let's shift now to the economic side of this story because encryption isn't the only reason governments are pouring billions into this technology. Fault-tolerant quantum computers promise genuine breakthroughs in fields that classical supercomputers simply cannot touch efficiently, and Japan's own roadmap explicitly names materials science as its first priority application. Simulating how molecules and materials behave at the quantum level is exactly the kind of problem quantum computers are naturally suited for, because you're essentially using quantum mechanics to simulate quantum mechanics, rather than approximating it with brute force classical calculation. That has enormous implications for industries Japan already dominates. Better battery, chemistry for electric vehicles, new catalysts for cleaner industrial chemical processes, advanced materials for next-generation semiconductors, an industry where Japan is fighting hard to reclaim relevance after decades of losing ground at Taiwan, South Korea, and the United States. Pharmaceutical companies are watching closely too, because drug discovery involves simulating how complex molecules interact with biological targets. A computational problem so difficult that even the world's fastest classical supercomputers, including Japan's own Fugaku system, struggle to model it accurately at scale. That Fugaku connection matters more than it might seem. Fujitsu co-developed Fugaku, one of the most powerful classical supercomputers ever built, and the company has explicitly stated its intention to integrate its next-generation high-performance computing platform, built around its Monica processor line, with its quantum computing efforts. This is the hybrid classical quantum integration strategy that's becoming the industry's dominant approach worldwide. Japan is positioning itself to own both halves of that stack simultaneously. The classical supercomputing side through Fugaku's successors, and the quantum side through the Fujitsu Reiken roadmap. Very few countries can credibly claim leadership in both categories at once, and that dual capability is exactly what makes Japan's position so structurally strong compared to countries chasing quantum computing without a comparable classical supercomputing base underneath it. Now let's talk about the startup ecosystem underneath the big corporate names, because this is where Japan's strategy gets genuinely interesting, and where a lot of English language coverage completely drops the ball. Fujitsu and Reiken dominate the headlines, but Japan's quantum ecosystem now includes more than 50 tracked organizations, spanning superconducting, trapped ion, photonic, and annealing-based approaches simultaneously, a level of technological diversity that few other countries are pursuing at once. Take Qubit Core, a startup led by CEO Ruta Watanuki, working on Japan's first trapped ion quantum computer, an entirely different physical approach from Fujitsu's superconducting systems. Qubit Core raised pre-seed funding in January 2025, and by April 2026 had closed a 1.53 billion yen seed round led by SBI Investment. Their roadmap targets a testbed system by 2028, a 1,000 qubit prototype by 2029, and commercial deployment by 2030, running out of a research center at the Okinawa Institute of Science and Technology. Trapped ion architecture tends to offer higher qubit fidelity than superconducting systems, though historically at the cost of speed, so having a credible domestic trapped ion player alongside Fujitsu's superconducting bet gives Japan genuine technological hedging, rather than putting the entire national strategy on a single physical approach that might hit an unexpected engineering wall. Then there's OptQC, pursuing optical quantum computing, a photonic approach that made enough of an impression internationally to earn a feature in the Financial Times special report on Japan's quantum ecosystem, which described the rapid advancement of quantum technology across the country as driven by tight industry academia government collaboration and a wave of ambitious startups entering the field amid intensifying global competition. Add in software and applications companies like BlueCat and Fixstars Amplify, working on the algorithm and use case layer that will eventually let ordinary businesses actually run workloads on these machines once they're ready, and you start to see a full stack national ecosystem forming, not just one flagship hardware project chasing headlines. It's also worth mentioning NEC here, because the company holds a claim to quantum history that almost nobody outside the field remembers. Back in 1999, NEC researchers demonstrated the world's first solid-state qubit, a charged qubit built inside a superconducting circuit, a breakthrough that laid essential groundwork for the entire superconducting qubit approach that companies like Google, IBM, and yes, Fujitsu all eventually built their empires on. Japan didn't just show up late to this race and throw money at it. It has technical roots in quantum hardware research stretching back over 2 decades, roots that are now finally being matched with the kind of serious capital and coordinated national strategy needed to turn early scientific leadership into commercial and strategic dominance. Let's zoom back out now and put all of this into a wider global context. Because Japan's roadmap update doesn't exist in a vacuum, it's landing in the middle of what analysts are now openly calling a genuinely global quantum arms race. The United States is in the process of reauthorizing its national quantum initiative with billions of dollars in fresh funding. The European Union's quantum flagship program is deploying roughly 1 billion euros across the continent, with individual member states layering on their own massive commitments. France at 1.8 billion euros, Germany at 3 billion euros. The United Kingdom recently announced up to £2 billion in quantum investment, explicitly framed by officials as one of the most significant government commitments to the technology anywhere in the world. Canada and Finland are staking out their own positions too. Against that backdrop, what makes Japan's approach distinctive isn't the size of the E. Check, plenty of countries are writing bigger ones. It's the depth of vertical integration and the speed at which public and private actors are moving in lockstep. Analyst Ulrike Scheide, writing for the National Bureau of Asian Research, described Japan's approach as building world-class infrastructure for next-generation computing through public-private collaboration, calling it something of an exception in an era when most countries are locked into zero-sum technology competition rather than genuine coordinated national strategy. That framing matters. While other nations are still arguing about funding levels and organizational structure, Japan already has its universities, its national research institutes, its flagship corporations, and its startup ecosystem all pulling in the same direction, aimed at the same fiscal year 2030 milestone. That kind of coordination is genuinely rare, and it's worth pausing on why. In the United States, quantum research is split across university labs, venture-backed startups, and a handful of tech giants who are often direct commercial rivals with little incentive to share breakthroughs. In China, the effort is largely state-controlled and much less transparent to outside observers, which creates real uncertainty about how much genuine progress is actually happening behind closed doors versus how much is strategic signaling. Japan's model threads a different needle entirely. Government funding flows through clearly defined national programs like Moonshot and Q-Leap, but the actual research execution happens inside a tight, cooperative network of corporations and roadmap slippage across every country and every company pursuing it. Google, IBM, and a long list of well-funded startups have all pushed back major milestones multiple times over the past decade, and there's no obvious reason Japan's 10,000 qubit target is somehow immune from the same engineering challenges that have humbled everyone else who's tried this before. Building and maintaining 10,000 physical qubits simultaneously, keeping them all cooled to near absolute zero, controlling them with enough precision to run coherent error correction across the entire system, and doing it all by a fixed fiscal year, is an engineering challenge on a scale genuinely comparable to some of history's most ambitious infrastructure projects. Individual control lines without the system becoming impossibly expensive or physically unwieldy, and the decoding algorithms needed to actually catch and correct quantum errors in real time, fast enough to keep pace with a live computation, remain an active and unsolved area of research, not a finished piece of engineering sitting on a shelf waiting to be deployed. Out to be far less useful in practice than the press releases implied. Still, even a partial success matters enormously here because the 250 logical qubit target for 2030 is specifically chosen to be useful, not just impressive. Researchers widely believe that once you cross into the range of a few hundred stable logical qubits, you unlock genuinely valuable materials, science and chemistry simulations that classical supercomputers simply cannot run in any reasonable amount of time, even with machines as powerful as Fugaku. That's the threshold where quantum computing stops being an academic curiosity and starts becoming an actual industrial tool that pharmaceutical companies, battery manufacturers, and materials scientists can build real products around. Japan isn't trying to win a symbolic qubit count headline. It's trying to cross the specific threshold where the technology starts paying for itself economically, and that distinction is exactly why serious industry analysts are treating this roadmap update as meaningfully different from earlier quantum computing. Stacked domestically, from raw qubit fabrication through classical supercomputing integration, through eventual industrial application, insulating itself from the kind of export control disruption that increasingly threatens international technology partnerships in a more fragmented geopolitical environment. South Korea is betting on speed and international partnership, importing the best available Western hardware today and layering Korean industrial application and capital on top of it, accepting the geopolitical exposure that comes with depending heavily on American firms in exchange for a faster path to commercial deployment. China is betting on scale and state control, treating quantum computing as inseparable from national security policy and pouring in resources at a level that dwarfs its neighbors, while accepting less international scrutiny and transparency than either Japan or Korea in exchange for tighter strategic control over its own program. None of these three approaches has definitively proven superior yet, and honestly, it may take until close to the end of this decade before we know which strategic bet actually paid off. But Japan's latest roadmap update matters right now because it's the clearest, most concrete, most technically detailed public commitment any of the three countries has made toward an actual fault. By contrast, just told the entire world exactly what it's building, exactly which architecture it's using, exactly which research institutions are involved, and exactly which fiscal year it expects to hit its target. That kind of specificity is rare in an industry that has historically thrived on vague, ambitious-sounding announcements with soft, shifting deadlines. And it's precisely that specificity which is forcing competitors across the region to recalibrate their own public roadmaps and funding announcements. Because Japan just raised the bar for what a credible national quantum strategy is actually supposed to look like on paper. Whether Fujitsu hits fiscal year 2030 exactly on schedule almost matters less than the fact that Japan has now set a concrete, falsifiable benchmark that every other country in the region will inevitably be measured against, publicly, for the rest of this decade. If you're new to this channel and you want to understand where the global technology race is actually headed, not just the headlines and everyone else is covering, make sure you subscribe, because we're breaking down exactly these kinds of shifts as they happen before mainstream coverage catches up and before most of the mainstream financial press even realizes these stories are connected to each other at all. One more angle deserves attention before we wrap this up: the growing convergence between quantum computing and artificial intelligence, because these two technologies are increasingly being discussed as intertwined rather than separate frontiers. Researchers across Japan's quantum ecosystem, including teams working alongside Fujitsu and Riken, have begun exploring hybrid quantum classical machine learning approaches, where quantum processors handle specific narrow subtasks, like optimization problems or certain kinds of pattern recognition, while classical AI systems handle everything else. Nobody credible is claiming quantum computers will replace today's large language models or generative AI systems anytime soon. The physics and the use cases are simply too different for that kind of direct substitution. But the emerging consensus among researchers is that quantum-accelerated components could eventually speed up specific bottlenecks inside AI training and inference pipelines, particularly around complex optimization and certain categories of simulation that classical processors handle inefficiently. Given how much global attention and capital is already flowing into artificial intelligence infrastructure, any credible pathway connecting quantum computing to AI acceleration adds yet another layer of strategic urgency to Japan's roadmap, because it means the country isn't just racing to win a standalone quantum computing prize, it's positioning itself to plug directly into whatever the next generation of AI infrastructure ends up requiring. This also connects back to the 6G telecommunications angle mentioned earlier, since next-generation wireless infrastructure is expected to rely far more heavily on distributed AI processing at the network. Edge and quantum-secured communication links are increasingly discussed as a foundational requirement for that kind of infrastructure once it reaches genuinely sensitive government, financial, and industrial applications. Japan's major telecom carriers are already coordinating quantum key distribution trials with exactly this future, network architecture in mind, rather than treating it as an isolated cybersecurity project, disconnected from the country's broader 6G ambitions. That kind of long-horizon infrastructure planning, tying quantum security directly into next-generation telecom rollout plans, years before either technology is fully mature, is another example of the coordinated multi-decade thinking that distinguishes Japan's current strategy from earlier, more scattered attempts at technology leadership across other industries and other eras. International reaction has been notable too, even beyond the immediate Asian competitors already covered here. Officials and analysts connected to the United States National Quantum Initiative have publicly acknowledged Japan's coordinated model as a genuine point of comparison worth studying, given persistent structural criticism that American quantum funding remains too fragmented across competing agencies, universities, and private companies, with limited built-in coordination mechanisms. European quantum policy circles, particularly inside Germany and France as they deploy their own multi-billion euro national programs, have likewise referenced Japan's public-private collaboration model as a structural template worth studying, even while pursuing very different funding levels and technical approaches of their own. When policymakers in Washington, Berlin, and Paris start explicitly referencing a rival's coordination model as worth emulating, that's a much stronger signal of genuine strategic respect than any single funding announcement could ever provide on its own. Let's close by connecting this back to something bigger than qubits, funding numbers, and fiscal year targets, because at the end of the day, this story is really about who gets to write the rules for the next era of computing. Every major technological shift in modern history, from the internet to mobile computing to artificial intelligence, has rewarded the countries and companies that controlled the foundational infrastructure early, not necessarily the ones that shouted the loudest about it. Quantum computing is shaping up to be the next infrastructure layer, sitting underneath encryption, materials science, drug discovery, and eventually artificial intelligence training itself, since researchers are already exploring how quantum processors might eventually accelerate certain categories of machine learning workloads that classical hardware struggles with. Japan spent decades being described, sometimes unfairly, as a country that invented brilliant technology and then somehow failed to commercialize it fast enough to keep pace with more aggressive competitors. That reputation shaped how outside observers, including plenty of Western analysts and investors, discounted Japan's chances in earlier technology races well before those races were actually decided. And it's worth remembering how often that discount turned out to be wrong once the full multi-decade picture eventually became clear. This roadmap update, backed by trillion-yen government budgets, a genuinely coordinated public-private research ecosystem, a diversified startup landscape, hedging across multiple qubit technologies, and a level of engineering specificity that most rival programs still haven't matched, reads like a deliberate attempt to make sure that particular historical pattern doesn't repeat itself with quantum computing. Whether that bet pays off by 2030 remains genuinely uncertain, and anyone telling you they know for certain how this plays out is overselling their own confidence. Physics doesn't care about press releases or fiscal year targets. Cryogenic engineering at this scale has humbled better-funded programs before, so healthy skepticism alongside genuine attention is exactly the right posture to hold as this story continues unfolding over the coming years. But one thing is already clear right now, today, in 2026. Japan just forced every other serious player in the Asian quantum race, and honestly, every major government watching from outside the region too, to take its ambitions seriously in a way they simply weren't doing 18 months ago. And that shift in perception, more than any single qubit count or funding figure, might end up being the most consequential. It's worth pausing here to address the history lesson everyone in Japanese industrial policy circles is thinking about but rarely says out loud. Japan dominated global semiconductor manufacturing in the 1980s, only to watch that lead erode over subsequent decades as Taiwan and South Korea outinvested and out-executed on advanced chip fabrication. Japan also famously lost the home video format war of the same era, when Sony's technically superior Betamax lost out commercially to VHS, largely because of licensing strategy and industry coordination rather than raw engineering quality. Those two historical episodes sit quietly behind almost every conversation about Japanese industrial strategy today, and they help explain why the current quantum push looks so different in structure from those earlier eras. This time, the government isn't leaving standardization, licensing, and cross-industry coordination to chance or to a single company's commercial instincts. The 60-company consortium, the trillion-yen coordinated budget, and the Riken Fujitsu. Fujitsu's stock and its broader technology division have drawn increasing attention from institutional investors, specifically tracking quantum computing exposure. a sector that remains largely speculative for publicly traded companies almost everywhere else in the world. Because Fujitsu is a large, diversified, already profitable technology conglomerate rather than a single-purpose quantum startup burning through venture capital with no other revenue streams, it offers investors a fundamentally different risk profile than betting directly on companies like IonQ or Rigetti, whose valuations rise and fall almost entirely on quantum-specific sentiment, speculative future potential. Analysts covering the sector have started describing Fujitsu's approach as a hedged way to gain quantum computing exposure without betting the entire investment thesis on a single unproven technology succeeding on schedule, since the company's semiconductor, supercomputing, and enterprise software businesses continue, generating stable revenue regardless of how quickly the quantum roadmap actually progresses. That distinction matters for how seriously financial markets are treating this announcement compared to typical quantum computing headlines. When a pure-play quantum startup announces an ambitious roadmap, markets have learned to apply a heavy skepticism discount because the company's survival often depends on hitting exactly that roadmap to justify further funding rounds. When Fujitsu extends its existing, already funded quantum program with more specific milestones, backed by an already profitable multinational balance sheet and direct government co-funding through NATO, the credibility calculus looks completely different. It's the difference between a startup promising a moonshot and an established aerospace company extending an already active satellite program. Both are ambitious, but only one of them has the existing infrastructure, cash flow, and institutional track record to make the deadline genuinely credible rather than aspirational. Breakthroughs, control electronics redesigns, and quantum error decoding advances, each expected to be demonstrated incrementally rather than all at once at the very end. Industry analysts tracking the project closely expect visible progress reports roughly on an annual cadence, meaning viewers interested in this space should expect a steady drumbeat of smaller announcements between now and the end of the decade, rather than total silence followed by one final unveiling. Each of those smaller milestones will offer a genuine, verifiable signal about whether Japan is actually on pace, or whether the kind of slippage that has haunted competitors elsewhere in the industry is starting to creep into this program as well. Watch specifically for updates around the NATO-backed post-5G infrastructure project, since that funding structure runs through fiscal year 2027 and effectively marks the halfway checkpoint toward the full 2030 target. If Fujitsu and Riken hit their interim goals inside that window, expect renewed confidence and probably accelerated investment from both government and private partners. If that checkpoint slips significantly, expect exactly the kind of quiet roadmap revision that has quietly affected almost every other ambitious quantum computing timeline announced anywhere in the world over the past decade. Either outcome will tell us something important, not just about Fujitsu specifically, but about whether Japan's entire coordinated national model for technology development can actually outperform the more fragmented approaches being run in the United States, South Korea, and China. Let's dig a little deeper into the industrial coalition standing behind this roadmap, because Fujitsu and Riken are really just the visible tip of a much larger corporate iceberg. Toyota Systems has already deployed Fujitsu's digital annealer technology in production, achieving a 20 times acceleration on automotive connector design workloads running on standard computing hardware, a practical demonstration that quantum-inspired computing is already delivering measurable industrial value today. Years before the fault-tolerant machine even exists, Hitachi is running its own parallel effort in silicon spin qubit technology alongside quantum annealing research, giving Japan yet another independent hardware pathway beyond superconducting and trapped ion approaches. Toshiba, Sony, and Mitsubishi Electric all maintain active quantum research programs as well, alongside Hamamatsu Photonics, a company whose specialized photonic detectors and components have quietly become critical infrastructure for quantum experiments in laboratories worldwide, not just inside Japan. That last point matters more than people realize. Hamamatsu isn't building a quantum computer of its own, but it supplies some of the precision optical and photon detection hardware that photonic and optical quantum computing efforts around the planet depend on, including companies well outside Japan's borders. That gives Japan a quiet, easily overlooked form of leverage in the global quantum supply chain, similar to how the country dominates specific niches of semiconductor manufacturing equipment without necessarily building the most famous end products itself. If you're mapping out who actually controls the physical supply chain underneath the quantum computing industry, Japan's fingerprints show up in far more places than the Fujitsu Riken headline roadmap alone would suggest. There's also an industry consortium worth mentioning here, a coalition of more than 60 Japanese companies coordinating on quantum standardization, application development, and supply chain resilience. Standardization sounds boring compared to a 10,000 qubit machine, but it's exactly the kind of unglamorous groundwork that determines whether a country's technology becomes the global default or ends up as a locally successful but internationally irrelevant dead end. Japan learned this lesson the hard way with certain in consumer electronics formats decades ago, where brilliant engineering lost out commercially because of fragmented standards and slow international coordination. The Quantum Consortium looks like a deliberate attempt to avoid repeating that exact mistake this time around, making sure Japanese quantum hardware, software, and error correction approaches are compatible enough with international systems to actually get adopted at scale rather than staying a domestic curiosity. Now let's talk about the conference circuit, because that's often where you can feel industry momentum shifting before it shows up in official roadmaps. Q2B Tokyo, one of the most closely watched quantum computing conferences in the world, has grown rapidly over the past 2 years, drawing major players like Honda's research and development division alongside dedicated quantum computing firms. The tone at these events has visibly shifted. A year or two ago, presentations leaned heavily on theoretical potential and long-term promises. The most recent sessions instead focused on concrete product roadmaps, measurable technical progress, and expanding commercial partnerships across the wider Asia-Pacific region. That shift in tone, from theoretical promise to product roadmap, is exactly the kind of signal that tells you an industry is maturing out of its purely academic phase. D-Wave's decision to launch its first ever Qubits Japan conference is another data point worth noting, driven by an 83% increase in bookings for its annealing quantum computing technology across the Asia-Pacific region, as organizations increasingly explore optimization and quantum-assisted artificial intelligence applications. That's a foreign company choosing to build dedicated Japanese market infrastructure, specifically because commercial demand inside the country is growing faster than it can serve remotely. When international quantum vendors start setting up dedicated regional operations inside Japan, rather than simply exporting hardware from North America, that's a meaningful signal about where genuine commercial appetite for this technology is actually concentrated within Asia. Let's also address something that rarely comes up in mainstream coverage of the S topic: talent and education. Building a 10,000 qubit fault-tolerant quantum computer isn't just an engineering problem, it's a human capital problem, and it requires an entire generation of physicists, cryogen IC engineers, and quantum software developers who currently don't exist in nearly sufficient numbers anywhere on Earth. Japan's universities, led by the University of Tokyo and Osaka University, working alongside RIKEN, have been steadily expanding dedicated quantum information science programs specifically to feed this pipeline. The 10 million user target for 2030 isn't just about deploying hardware either. It implicitly requires training enough software developers, researchers, and industrial engineers who actually know how to write and run quantum algorithms, a workforce challenge that may ultimately prove just as difficult as the hardware itself. This is actually one of the quieter but more interesting angles of Japan's strategy compared to some competitors. China's enormous investment numbers can theoretically buy hardware and infrastructure relatively quickly through sheer capital deployment. What money alone struggles to buy quickly is a deep, experienced talent base capable of actually operating and improving that hardware once it's built. Japan's decade-long tradition of precision engineering education, combined with the RIKEN Fujitsu Collaboration Center's explicit design as a training ground where students and corporate engineers work literally side by side on live projects, gives the country a talent development advantage that doesn't show up cleanly in any funding comparison table, but which could end up mattering enormously once these machines actually need skilled people to run them at scale. There's also a quieter defense and security dimension layered underneath all of this that rarely makes it into consumer technology. Coverage, quantum key distribution, a method of using quantum mechanics itself to detect any attempt to intercept a communication, is being actively developed and tested inside Japan as a complementary technology alongside fault-tolerant computing research. The logic here is straightforward. If quantum computers eventually threaten to break today's encryption standards, then quantum-based communication security becomes one of the few defenses that can theoretically stay ahead of that threat indefinitely, rather than simply being replaced by yet another mathematical algorithm that a future, more powerful quantum computer might eventually crack as well. Japan's telecom sector, including major carriers working alongside national research institutes, has been quietly testing quantum key distribution networks for exactly this reason, treating it as critical infrastructure rather than a laboratory curiosity. Layer in the semiconductor connection too. because it's impossible to fully separate Japan's quantum ambitions from its broader push to reclaim relevance in chip manufacturing. The same government budged T-Line's funding quantum industrialization in 2025 explicitly bundled semiconductor investment alongside it, reflecting an official recognition that these two technologies are deeply intertwined. Quantum computers need extraordinarily specialized control chips and cryogenic electronics, and Japan's push to rebuild domestic advanced semiconductor manufacturing capability, most visibly through the Rapidus Foundry project, directly supports. The custom chip demands that a scaled-up quantum computing industry is eventually going to need. That's a level of vertical integration between chips and quantum hardware that very few other countries are positioned to replicate quickly, because very few countries maintain serious, credible efforts in both categories simultaneously the way Japan currently does. Zoom out again, and you start to see the full picture forming. This isn't really a story about one company's 10,000 qubit target for fiscal year 2030. It's a story about a country deliberately rebuilding an entire technological ecosystem, spanning chips, quantum hardware, classical supercomputing, telecommunication security, industrial application, and workforce development, all pointed at the same strategic horizon. Individual pieces of that ecosystem existed before this latest roadmap update. What changed is the level of public specificity and coordination visible across all of them at once, which is exactly why competitors and analysts across the region are treating this moment as a genuine inflection point rather than routine corporate news. None of this guarantees Japan wins whatever you want to call the finish line of this race, because quantum computing may not even have a single finish line the way a sprint does. It's entirely possible multiple countries end up with genuinely useful, fault-tolerant systems within a few years of each other, each optimized for slightly different applications, industries, and security postures. But the countries and companies that move first typically shape the standards, the software ecosystems, and the commercial relationships that everyone else has to build around afterward. That first mover advantage, more than any single technical milestone, is what's actually at stake here, and it's why Japan's latest roadmap update deserves far more attention than the relatively quiet way it initially entered the news cycle. Think about how this compares to earlier technology races the world has already lived through. In every previous case, from the space race to the early internet build-out to the current AI infrastructure boom, the country or company that established the dominant technical standard first ended up shaping decades of downstream commercial and strategic advantage, long after the original novelty of the breakthrough had faded from public attention. Quantum computing looks poised to follow that exact same pattern, except this time the stakes touch something even more foundational than communication networks or computing speed: the mathematical trust underpinning the entire global financial and security system. That's precisely why a roadmap update from a Japanese technology company, buried in a press release most casual readers scrolled straight past, deserves to be treated as one of the more consequential technology stories of 2026, not a niche engineering footnote reserved for specialist publications. Years from now, people may look back at this exact moment as the point where the balance of the global quantum race quietly, decisively shifted. And that shift in perception, more than any single qubit count or funding figure, might end up being the most consequential outcome of this entire roadmap update. Perception drives capital. Capital drives talent flows. Talent flows determine which countries' labs make the next genuine scientific breakthrough first. Japan just planted a very public, very specific flag in that competition, and the rest of the region is now scrambling to figure out exactly how far behind or how close they actually are. Keep watching this space, because the next major update in this race, whether it comes from Beijing, Seoul, Washington, or Tokyo again, is going to move markets, reshape alliances, and quietly determine who controls the encryption protecting your data a decade from now, long before most people watching this video today ever notice the shift actually happening around them.